Okay, as I alluded to earlier, the arc lengths are more elegant in parametric form. So let's just consider this set of points that maybe were defined parametrically. All right, so there might be some curve, like I'm showing with the blue line, arcing between there, but we could connect these points as we did before with straight lines. So I have 3 segments being shown, but each one has a delta x and a delta y, and there is a delta L. Sometimes that's called delta S for arc length. I'll just be consistent with what I did before and call it delta L. So we can say exactly what we said before, that delta L squared, that's the hypotenuse, must equal delta x squared plus delta y squared. All right. Now, instead of dividing by delta x, if we're doing this parametrically, we would want to divide by delta t squared. Oh, and to be consistent, I should probably put parentheses around all of these things. So we can take our Pythagorean distance formula, divide by delta t squared, and we can see that delta L over delta t squared must equal delta x over delta t squared plus delta y over delta t squared, right? Now in MATLAB, we can simply figure out the delta L's from the square roots of both of the sides that I just boxed in. So we'll be able to do that for parametric equations. In fact, we're going to change the code that we had for functions defined, or y is defined as a function of x, into parametric equations, and be able to do exactly the same thing with that. But we want to consider, what would this look like when we get down to the calculus of this, all right? So if I want to look at the calculus of this, now we're going to have delta t approaching 0. As delta t approaches 0, well, what's true about delta x over delta t? That would become the same as the derivative of x with respect to time. Likewise, delta y over delta t would become the derivative of y with respect to time. Okay, so if we look at that, we could say from here that if I wanted to find, let me do another step here, let me bring this down. If I wanted to find delta L, I could say that delta L squared would equal the entire right-hand side that I have here, delta x over delta t squared plus delta y over delta t squared times delta t squared. And if I take the square root of all of that, I could say that delta L, that's one piece of it, would be the square root of delta x over delta t squared plus delta y over delta t squared times delta t. And if we apply what we have right up here, we can turn this into an integral to get the total length of the curve. In the case that delta t has gone to 0, the time steps are 0 in size, then the length of the curve would become an integral from wherever t equals a up to some final time. You could call those t0 and t final if you wish. And we would have the square root of dx dt squared plus dy dt squared, all integrated with respect to t. Now what's nice is this has a lot more symmetry. Notice how much symmetry it has. We don't favor x over y. They're symmetrically, they're the same in terms of importance. So we don't have a 1 showing up in the equation. So it's a little more elegant to work with this equation. There's another little ramification of all of this too. We won't delve into this too much, but if you're working with the parametric equation, we may want to know the slope of this at a given point. And so if we wanted to know the slope is still delta y over delta x, or as we close in on a point, the slope is still dy over dx. The second derivative gets a little complicated when you're working with parametric equations, but the first derivative can be found simply by taking dy dt and dividing by dx dt. So we need to know dy dt and dx dt in order to find the arc length. We could also find the slope anywhere by taking the ratio of dy dt to dx dt at any given t value, and that would give us the slope of the line.